Welcome to Math Zone African Motives. In this tutorial, we will be diving into a powerful technique for solving complex integrals. Integration by algebraic substitution. We will learn how to rewrite complicated integrands into simpler forms that we can easily solve. By the end of this video, you will be able to, first, identify suitable substitutions for various integral types. Second, apply a four-step procedure to evaluate integrals using this method. And third, handle cases where the derivative needs to be manipulated to fit the substitution. The main idea of substitution is to simplify an integral. We'll rewrite the function in terms of a new variable, u, to make it look like one of our basic integration formulas. Let's begin. We'll start with a common type of integral that substitution works well for, the type that looks like the integral of f of x to the power of n times its derivative f prime of x dx. This form might look familiar. In fact, if we see a function and its derivative in the integrand, we can often solve it just by looking at it, which is called integration by inspection. The formula for this is f of x to the n plus 1, all over n plus 1, plus our constant of integration, c. Substitution provides a formal method to prove this formula and handle more complex scenarios. Sometimes, the derivative part is multiplied by a constant. For example, k times f prime of x. This is also easily handled because we can pull the constant k outside the integral. Let's formalize the procedure we will follow. First, we identify a suitable substitution, which we'll call u, and then we find its derivative with respect to x du over dx. We then rearrange the equation to solve for dx. Next, we substitute u and our expression for dx back into the original integral. At this point, the integral should be entirely in terms of u and du. There should be no x's left. Third, we find the integral of the new, simpler expression in terms of u. This should be a standard integral that we know how to solve. Finally, we replace u with its original function in terms of x to get our final answer. Let's apply this procedure to an example. Our goal is to evaluate this integral. We need to evaluate the integral of cosine to the fifth of x times sine x dx. Following our procedure, step 1 is to identify our substitution, u. Look for a function and its derivative. We can see both cos x and sin x. Since the derivative of cosine x is negative sin x, a constant multiple of sin x, we will choose our substitution to be u equals cos x. Now we find the derivative of u with respect to x. The derivative of cos x is negative sin x. Rearranging to solve for dx, we get dx equals du divided by negative sin x. Step 2. Substitute these into our integral. We replace cosine x with u and dx with our new expression. Our integral becomes the integral of u to the fifth times sin x times du over negative sin x. Notice what happens. The sin x terms cancel out, which is exactly what we want. We've successfully eliminated all the x's from the integral. This leaves us with the integral of u to the fifth du with a negative sign in front. Step 3. Find the integral. This is a simple power rule integration. The integral of u to the fifth is u to the sixth over 6. So we have negative u to the sixth over 6 plus our constant c. Step 4. Replace u with its equivalent in terms of x. Since u was cosine x, our final answer is negative cosine to the sixth of x divided by 6 plus c. Let's verify this using our memo. It matches. Here's another example with a slightly different structure. We need to evaluate the integral of the natural log of x divided by x dx. Step 1. Identify u. Here we see a function ln x and its derivative, which is 1 x. This is a perfect setup for substitution. So we set it equal to ln. The derivative of u with respect to x is 1 x. Rearranging, we get dx equals x du. Step 2. Substitute into the integral. The integral becomes the integral of u over x times x du. Again, the x's cancel out. We are left with the integral of u du. Step 3. Integrate using the power rule. The integral of u du is u squared over 2 plus c. Step 4. Substitute back. Replacing u with ln x. Our final answer is the quantity ln x squared divided by 2 plus c. This matches the memo. Let's try another example where the substitution might not be immediately obvious. We need to evaluate the integral of 1 over x plus 1 over x dx. Here, there's no clear function and its derivative. So, step 1 is to simplify the integrand first. We can combine the terms in the denominator. A common denominator is x. So x plus 1 over x becomes x squared plus 1 all over x. Now we have a fraction inside a fraction. We can rewrite this by multiplying by the reciprocal of the denominator. Our integral becomes the integral of x divided by x squared plus 1 dx. Now this looks like the form f prime over f. We can make a substitution. Let's choose u to be the denominator, x squared plus 1. Step 2. Substitute these into our simplified integral. We replace x squared plus 1 with u and dx with do over 2x. This gives us the integral of x over u times do over 2x. As before, the x terms cancel out, simplifying the integral. We are left with 1 over 2u. We can pull the 1/2 outside the integral. Step 3. Integrate. The integral of 1 over u is the natural log of the absolute value of u. So we have min-div f times ln of u plus c. Step 4. Substitute back. Substituting u equals x squared plus 1, our final answer is 1/2 times ln of x squared plus 1 plus c. Since x squared plus 1 is always positive, we don't need the absolute value bars. The memo confirms this result. Now let's look at another important type of integral. This type is often called the logarithmic integral because its answer is a natural logarithm. It occurs when you have a function in the denominator and its derivative in the numerator. This pattern appears frequently, especially when working with trigonometric and exponential functions. Here's an example that fits this type 2 pattern. We need to evaluate the integral of cosecant squared x times cotangent x dx. Let's use our substitution method. First, we identify u. The derivative of cotangent x is negative cosecant squared x, which is a constant multiple of cosecant squared x. Therefore, we'll let u equal cotangent x. The derivative of u with respect to x is negative cosecant squared x. Rearranging for dx, we get dx equals do over negative cosecant squared x. Step 2. Substitute these into the integral. Our integral becomes the integral of cosecant squared x times u times do over negative cosecant squared x. The cosecant squared terms cancel. We are left with the integral of negative u do. Step 3. Integrate. This is a simple power rule. We get negative u squared over 2 plus c. Step 4. Substitute back for u. Our final answer is negative cotangent squared x divided by 2 plus c. This matches the memo. Now let's explore two more important types of integrals. These two types involve an exponential function, e to the power of a function f e x, or a constant a raised to the power of f each x. In both cases, the integral is straightforward if the derivative of the exponent f prime of x is also present. Let's work through an example of the exponential type. We need to evaluate the integral of e to the power of sin x times cos x dx. Following our procedure, step 1 is to choose u. Here, the exponent is our most complex part, and we can see its derivative right next to it. So we'll let u equal sin x. The derivative of sin x is cos x. This is great. Rearranging, we get dx equals do over cos x. Step 2, substitute into the integral. Our integral becomes the integral of e to the power of u times cos x times do over cos x. The cos x terms cancel out. We are left with the integral of e to the power of u do. This is one of the simplest integrals in all of calculus. Step 3. Integrate. The integral of e to the u is just e to the u plus c. Step 4. Substitute back. Our final answer is e to the power of sin x plus c. This matches the solution in the memo. Now for the manipulate and create the derivative part of our substitution procedure. Let's look at a problem where the derivative is not a perfect match. We need to evaluate the integral of x divided by cosine squared of x squared dx. Step 1. Simplify and choose u. The cosine squared in the denominator is difficult to work with. Remember that 1 over cosine is secant, so we can rewrite the integral as the integral of x secant squared of x squared dx. Now we can see a substitution. We'll let u equal x squared. Its derivative is 2x, which is a constant multiple of the x term we have. Rearranging for dx, we get dx equals do over 2x. Step 2, substitute these into our rewritten integral. We substitute x squared for u and dx for do over 2x. Notice the x terms cancel, and we are left with a 1/2 that we can pull out front. Step 3, integrate. We need to remember the standard integral of secant squared u. The integral of secant squared u is tangent u, so we have 1/2 tangent u plus c. Step 4, substitute back. Replacing u with x squared, our final answer is 1/2 tangent of x squared plus c. The memo confirms this is correct. Sometimes, a substitution might seem to work, but after you substitute back, you notice there's still an x term left. This means the substitution wasn't quite right. Let's work through an example that the memo shows with a 2-level substitution, and then I'll show you an alternative that is much faster. We need to evaluate the integral of cosine x divided by the quantity 1 plus sin x times ln of the quantity 1 plus sin x dx. The memo suggests a 2-step approach. First, let's substitute the inner function inside the logarithm. We set u equals 1 plus sin x. Its derivative is cos x, so dx equals do over cos x. Substituting this gives us the integral of 1 over u ln u du cp. Now we have a new integral that still needs solving. So we make a second substitution. We let v equal ln u. Its derivative is 1 over u, so do equals u dv. Substituting this into our new integral gives us 1 over v dv, which integrates to ln of v. Finally, substituting back twice, we get ln of 1 plus sin x plus c. As you can see, this is a bit lengthy. There's a faster way. When you see a logarithm of a function, it's often best to make the entire logarithm your substitution. Let's try a different approach. We'll set it equal to ln of 1 plus sin x. To find its derivative, we use the chain rule. The derivative of the outer function len of something is 1 over something. The derivative of the inner function, 1 plus sin x, is cos x, so the derivative is cos x over 1 plus sin x. Rearranging for dx, we find dx equals do times 1 plus sin x divided by cos x. Step 2, substitute this into the original integral. We substitute our u and our dx. Notice how beautifully everything cancels. The qstas icis, x terms cancel, and the 1 plus in x terms cancel. We are left with just the integral of 1 over u do. Step 3, integrate. Step 4, substitute back. This gives us ln of u plus c, which is ln of the quantity ln of 1 plus sin x plus c. We got the exact same answer as the memo, but in a much more direct way. This highlights the importance of choosing the right substitution. Let's tackle a final, challenging example. This integral looks very complicated at first glance, but with a clever substitution, it becomes much simpler. We need to evaluate the integral of the quantity x minus x to the negative 1, divided by x squared plus 2 ln of x to the negative 1. Step 1, simplify. That denominator is a mess. Let's simplify the logarithmic term using a log property. The property log of a to the power of b equals b times log of a is very useful here. So, ln of x to the negative 1 becomes negative 1 times ln x. Our denominator simplifies to x squared minus 2 ln x. The integral is now much clearer. It's a fraction where the numerator looks suspiciously like the derivative of the denominator. Let's choose u to be the simplified denominator. X squared minus 2 ln. Now we find its derivative. The derivative of x squared is 2x. The derivative of 2 ln x is 2 times 1 over x, or 2 over x. So, do over dx is 2x minus 2 over x. Rearranging for dx, we get dx equals do over the quantity 2x minus 2 over x. Step 2, substitute into the integral. This gives us the integral of our numerator term, divided by u times our expression for dx. It doesn't look like an immediate cancellation. Let's simplify the denominator of the dx term. We can pull a 2 out. 2 plus minus 2 over x is the same as 2 times the quantity x minus 1 over x. This is the same as 2 times our numerator term. Now let's rewrite the substitution. Our integral becomes the integral of x minus x inverse, divided by u times do over 2 times the quantity x minus x inverse. This time, the numerator term cancels perfectly. We are left with 1/2 times the integral of 1 over u do. This is a very simple integral. Step 3. Integrate. Step 4. Substitute back. The integral is 1/2 lengths of u plus c. Substituting our expression for u, the final answer is 1/2 times in of the quantity x squared minus 2 ln x plus c. This matches the solution in the memo. Let's quickly recap what we've learned. Integration by substitution is a powerful technique for simplifying integrals. The process involves 4 key steps: choosing a substitution u, substituting into the integral, integrating the simpler expression in terms of u, and finally, substituting back to get the answer in terms of x. We also saw that simplifying the integrand first and manipulating the derivative to fit the substitution are crucial skills to develop. Thank you for watching this tutorial from Math Zone African Motives. I hope this video has made integration by substitution clearer for you. Subscribe for more tutorials from Math Zone African Motives.